Alright, time for another draftphysics.com video presentation. So, responding to Ian Gosling's done now 3 videos regarding replicating the clay experiment he originally published with the wrong height dimension. So the idea is you're going to drop half mass from 4 times the distance, which would double its velocity, double its kinetic energy, and versus a 2 mass from 1 unit of distance. And the two things by momentum's theory, okay, by the fact that you will double the velocity, says that the two things should weigh the same. You hit the ground, they'll have the same collective force. One will have a higher velocity and a lighter mass, and one will have the commensurate opposite of the heavier mass and the lower velocity. And the total momentum being the same, and I would argue that means essentially the same weight. Impact weight. So, when he first did the experiment, he didn't talk about any irregularities or anything coming out wrong or any of that kind of stuff. When he did the measurements correctly, he was very concerned because the experiment was showing that, yes, it is the same weight. It is the same impact force. It creates the same amount of compression of a clump of clay. And now he's doing the experiment, and now it's not the same anymore. Now it's nowhere close to being the 2-to-1 that their theory predicts. And so they're arguing that it's, again, that somehow the clay is a spring, and it gets harder to compress somehow, okay, the more you compress it, which I don't think there's any rational physics to defend. There's just no reason it would get any more difficult to compress a piece of clay the more I compress it. It's the same difficulty to push the clay. It doesn't get any harder to push. But anyway, so he's getting numbers that are like this 1.4 thing again, okay, except the 1.4 doesn't apply in this case. So he's 0.6, okay, you could argue short. In terms of the amount of momentum. So somehow 0.6 okay, of the velocity has disappeared or something has gone wrong. Alright, so I guess I'll draw a couple of things. So he has improved the experiment slightly, but the big improvement that they don't seem willing or interested in doing is a release mechanism that's more consistent, more guaranteed, not to interfere in the experiment, and they just won't go there. And so maybe I'll explain some possible simple solutions and other things about how the experiment should be done or what experiments should be done, blah 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 blah. So no real need to play his videos. Again, he's getting a number like the 4 pounds dropped 1 foot, okay, is getting a number like to 35. He said, you know, it's a smaller amount of compression, 25 in terms of net displacement of the clay, and drop from the 2 mass drop from 4 times the height is coming out 25. So you got 35 versus you got 25 versus 35, and again, way short of 50, right? 35 is way short of 50. It's a simple way to understand it. And that's because they're saying that somehow clay is a spring. And I would argue that springs don't even do this 1.4 thing. But anyway, alright, so with that context, it's just, like I said, it was completely predictable that he's going to find a way to re-engineer the experiment to force the results to come out his way. He's now using a squared clump of clay. Probably doesn't make any difference, so I probably, you know, but whatever, you know, he'll just keep re-engineering the experiment and trying to get the results to push further and further in his direction. But anyway, yeah, we don't need this. Alright, so I did the, you know, it is all sort of, there's sort of mathematical requirements here that you just can't evade. So, you know, I figure it was worth just referencing that to some extent. That the number, it's in the numbers, so to speak. So you start off with 4 pounds here, and at 0, so it weighs 4 pounds. It's still going to weigh 4 pounds. This is still weighing 2 pounds. You can't change that fact. But what's interesting to note is that how much it weighs is just one behind, essentially. And it's not until you get to this, the velocity gets increased higher and higher. This is the 1 foot. This is the 1 foot weight. 128 pounds. So you drop it 1 foot, it'll weigh 128 pounds. And it's based on just the simple idea that for every the first centimeter doubles your weight. The 4 centimeters, quadruples your weight. And it just keeps on going like that. It doubles your doubled weight. I'm sorry. It doubles and it doubles and it doubles for every 4 units of extra distance. So you can see there's a huge differential. 1 foot and 4 feet, are just these two numbers. You're just doubling your weight, but it's a gigantic difference in distance. So it's like all right here. I mean, the entire difference between 1 foot and 4 foot is in this one set of numbers. So you can sort of understand that if you don't quite, if you let go of the weight and you lose, this is only a 3 or a 2 instead of a 4, then all these numbers are perverted pretty dramatically in terms of you're not going to get your complete weight. So a little bit of flaw in the distance they're allowed to fall makes more difference than you might think it does, okay, because of this quadratic growth in the velocity and distance traveled. Not in the velocity, but in the distance traveled. All right. So just saying, it's quite interesting to see the difference in the two. This should be 128. So I made a mistake. 128. Okay. Double the weight here. So the 128 would be after the 4 feet. The 1,000 centimeters versus the 1,000 here that never reaches, and it just goes 250 centimeters for the 1 foot. So, huge difference, same weight though. So, and it's all kind of Galilean, kind of structured math. You can't really fudge it anywhere. Where are you going to get this kinetic energy thing from? The momentum's pretty obvious, and the connection between the momentum and the weight is pretty obvious. So I would argue that that's, I don't really see how there's much room to argue the case, but whatever. Alright, so to get to the experiment, so we did add a plate at the bottom that he puts inside the other, a tube he puts inside the other tube. Okay, so, and frankly that's a kind of a good idea because it at least creates a flat surface to be pushing the clay. Now it could be a bigger flat surface because the clay still sticks out a little more than the surface does, and now he's, like I said, using a square piece of clay. But shouldn't make that much of a difference. But what he should be doing is, since he's dropping the one weight from 4 times the distance. So again, you drop the 4 pounds from 1 unit of distance. You drop the 2 pounds, okay, from 4 units of distance. All right, and so it technically, by kinetic energy, we're collecting the energy in the motion and the squishing of the clay. The movement of the clay particles is using up the energy, okay, in a way that we can see the use of the energy. And the assumption is that it's sort of connected. The amount of pressure you put on is seen in movement of clay without much bias regarding how fast you push it or how slow you push it. It's just about pushing little pieces of clay, and it hopefully doesn't make much difference. Now we already know that it makes a huge difference if I push on a piece of wood, that if I go at a high velocity and I hit a small surface area, I'll shatter the wood, okay, and break it. But if I apply the force over a large area, or I apply it slowly, okay, a slow amount of heavy force, the board won't break. So there are substances that have biases, and we're just hoping that clay doesn't have one of those biases. So anyway, but the simple experiment what to do is just to take this 2 mass and drop it from 1 foot and see if you get what you should get, which is twice the compression of the clay. Alright, so you're basically doubling the velocity, doubling the momentum, and if it was a car, it would crush twice as much. Those are the facts that have already been established by other experiments. So that would be the prediction of momentum science. So do that experiment. I guess by their prediction, this should compress, since this will have twice the velocity still. This should be from 1 foot, it should be yeah, 4 times. So this should be compressed a lot less, because this is going to be the same weight. It should be, by their theory, this should be 4 times the compression. So their theory says this should be 4 times the compression. So there should be 4 of these in that. Okay. So good luck with that experiment, frankly, and we'll see. Do that one too. It's kind of simple since you already got the materials. Now dropping the 4 from the 4, yeah, that might be a little more tricky. I mean, you probably can do it without breaking something, but who knows? So that would be the other point. There's a point where you also have to concede that if you are getting some differentials, that his table might not be exactly as firm as it needs to be, and so it could be yielding a little bit under what are substantial pressures. I mean, 250 pounds. It's 128 pounds. Okay. For the 4 mass dropped 1 foot, and it's 128 pounds supposedly for the 2 mass dropped 4 feet. But obviously if you drop the 4 mass from 4 feet, then you go up to 256 pounds. So it's a pretty good jump. Alright, so what else did I have to say? Yeah, so it would be nice for him to try the spring thing again, and put a spring underneath there, and then we just have to figure out some way to measure how far the spring was compressed before it gives back the energy, the bounce. It'd be nice to see the bounce, just how much energy the spring destroys would be also interesting to see. And all of that will be dependent again upon surfaces. The harder the surface that you have the spring mounted to, the more energy you get back, okay? Because the more you allow this surface to yield, the less the spring can give back. So that's always a good example of whether the spring is working properly, is how much energy you give back. If it loses half the energy, well then there's something wrong with your mechanism. But yeah, the idea is, so when the spring is compressed, as the object pushes down into the spring and compresses it, it'd be nice to be able to have some little simple light mechanism that is also bent, also changed by the impact, but it's changed by a few ounces hitting it, so it's not taking away. 128 pounds is a lot. So the other thing that I brought up in previous videos is you have to subtract the actual weight. Okay, the actual weight of the 4 pounds has to technically be subtracted, and the actual weight of the 2 pounds from the result, because that's the static weight. That's not what you're trying to measure. You're measuring the impact weight, the weight collected by dropping, not the weight collected by standing on the clay. But you can see how it doesn't make much difference. 4 pounds from 128, isn't going to make much difference in the outcome. It's a 1% kind of thing. It's a very small change. So the difference between 126 and 124 isn't going to be enough to be even noticeable, frankly. Let's see what else. But yeah, so variations of the experiment would be good. So people should just think about how to measure the farthest that something moves. Whether that's by putting something. You can think of like little sticks, and you could just hit the little sticks, or some kind of, but it has to be light You have to be able to reset it easily. I mean, you could put like a little lever and then put a strip of clay on a surface, and then the little lever which would, rip the clay to a certain height, and then you could just measure that. There's got to be some kind of easy mechanism where, some kind of simple mechanism that tells you how far something was moved and stays there, so you can see how far it went down. Now, if we had great video equipment, I guess we wouldn't need it, but nobody has. I mean, physicist Michael has his, his, whatever those are called, not an iPhone, but the other one, and it does the 970 frames per second, only does it for whatever, 20 seconds, but it's pretty good. Anyway, yeah, so I think that's it I have for at this moment that needs to be considered. But yeah, again, so it's fine. It's more experiments, the better. But again, I would argue that, the quick release. I'm just saying that one's kind of simple, because all you have to do is have a string that goes the length, and you just put a knot at 1 foot with a little hook, and then a knot at 4 feet with a little hook, and then you just make a little basket for the weight. You just, the weight is this shape. You just put string around this way and string around that way around the bottom of the weight. Okay, and then you can basically hold the weight up by just using, once you've made the basket. Let me draw that. So you basically are suspending, the weight, by string going underneath it. Okay, so you've suspended it. Now you can put it on a string, right? And then you can have a loop in the string, and then you just put another loop in it, to hook onto the hook. And then you can just cut this loop. So you just make a bunch of loops that are the same size, that are the right size for when it's on this hook, and then you can just cut those and cut those and cut those, reset the weight, put it on the hook, and then just cut the loop, and you have a standard dropping mechanism that's going to be much more reliable. Because frankly, I think when he's dropping the 4 pounds, he can't get his hand out of the way nearly fast enough. It's 4 pounds, pretty hard to instantly drop it. Okay, so we'll leave it short and not too unsweet. I'm just sick of arguing this personality crap. This is real physics. I mean, again, these are people who won't concede that their physics should have done all these experiments already. We shouldn't. In 2023, we shouldn't be having an argument about how much 2 pounds dropped 4 feet weighs. I mean, these should be already established numbers, well established. So this is a whole conversation shouldn't be taking place if their physics was good science. And it's clearly not good science. And again, I can go through the whole history of all the bad assumptions. Stephen Breaux is still defending denting clay with round objects. He's still defending that as somehow being a legitimate measure of total energy, when I've already explained quite completely how it's obviously not good theory. But anyway, so is the nature of communication with humans. Very unsatisfactory. I get something to work right here. Anyway, till the next time, and such and so forth and whatnot. Well, I think that's enough.